Welcome to the calm cosmos, in the vast silent theatre of the cosmos, where stars are born in nebulae of gas and dust, live out their lives in brilliant fusion, and eventually fade. There are some celestial objects whose demise is not a gentle whisper, but a cataclysmic roar. For the most massive stars, their death marks not an end, but a spectacular transformation into some of the universe's most extreme and enigmatic entities, neutron stars. The calm cosmos, in its grand cycle of creation and destruction, reveals wonders beyond our wildest imagination. To understand a neutron star, we must first understand the life and death of a massive star. Stars, like our Sun, spend the majority of their lives in a state of hydrostatic equilibrium, a delicate balance between the outward pressure generated by nuclear fusion in their core and the inward pull of their own immense gravity. In their cores, hydrogen atoms fuse to form helium, releasing enormous amounts of energy that radiate outward, preventing the star from collapsing. The calm cosmos, in its stellar furnaces, continuously transmutes matter into energy. However, this fusion process cannot continue indefinitely. For stars much more massive than our Sun, typically 8 times the Sun's mass or more, as the hydrogen fuel in their core depletes, they begin to fuse heavier elements. Helium fuses into carbon, carbon into oxygen, and so on, up the periodic table. Each successive fusion stage requires higher temperatures and pressures and produces less energy. This process continues until the star's core is primarily composed of iron. The calm cosmos, in its stellar alchemy, creates the building blocks of the universe. Iron is a crucial turning point because, unlike lighter elements, fusing iron does not release energy. It consumes energy. Once the core is made of iron, nuclear fusion ceases to be a source of outward pressure. With no outward force to counteract the immense inward pull of gravity, the core begins to collapse catastrophically. This collapse happens incredibly rapidly, in a matter of milliseconds, as the core shrinks from a size comparable to Earth to a mere few tens of kilometers across. The calm cosmos, in its gravitational might, orchestrates the ultimate stellar implosion. This rapid collapse is so violent that it causes the outer layers of the star to rebound off the superdense core, creating a shock wave that propagates outward. This shock wave, combined with a flood of neutrinos, tiny, nearly massless particles that interact very weakly with matter, blasts the star's outer layers into space in a spectacular explosion known as a Type II supernova. For a brief period, a single supernova can outshine an entire galaxy, releasing as much energy as the Sun will produce over its entire 10 billion year lifetime. The calm cosmos, in its cosmic fireworks, illuminates the vast darkness. What remains after this cosmic detonation is the incredibly dense, collapsed core of the star, the neutron star. If the initial mass of the star's core was between about 1.4 and 3 times the mass of our Sun, a limit known as the Chandrasekhar limit for white dwarfs, but extended for neutron stars, the gravitational collapse is halted by a phenomenon called neutron degeneracy pressure. The calm cosmos, in its extreme conditions, reveals the exotic states of matter. Under the immense pressures of the collapsing core, electrons are forced into atomic nuclei, where they combine with protons to form neutrons. This process, known as inverse beta decay, effectively transforms the entire core into a giant atomic nucleus, composed almost entirely of neutrons. These neutrons are packed together so tightly that they resist further compression, creating an outward pressure that can finally counteract the inward pull of gravity. The calm cosmos, in its subatomic transformations, creates a new form of stellar remnant. A neutron star is an object of unimaginable density. A single teaspoon of neutron star material would weigh billions of tons, more than all the cars and trucks in the United States combined. Despite having a mass greater than our Sun, a neutron star is incredibly small, typically only about 20 kilometers, 12 miles, in diameter, roughly the size of a city. This makes them the densest objects in the universe, second only to black holes. The calm cosmos, in its compact wonders, defies our everyday understanding of matter. The surface gravity of a neutron star is also extraordinarily strong, billions of times stronger than Earth's gravity. If you were to drop an object onto a neutron star, it would hit the surface at a significant fraction of the speed of light, releasing an enormous amount of energy. The escape velocity from a neutron star is about half the speed of light, meaning anything trying to leave its surface would need to be travelling at an incredible speed. The calm cosmos, in its gravitational extremes, creates environments where the laws of physics are pushed to their limits. Neutron stars are also characterized by their incredibly rapid rotation. As the star's core collapses, it conserves its angular momentum, much like a spinning ice skater who pulls their arms in and spins faster. A star that once rotated slowly over days or weeks can collapse into a neutron star that spins hundreds of times per second. The fastest known neutron star, PSRJ 1748-2446 AD, rotates at an astonishing 716 times per second. The calm cosmos, in its cosmic gyroscopes, spins with incredible velocity. Furthermore, neutron stars possess incredibly powerful magnetic fields, billions to trillions of times stronger than Earth's magnetic field. These fields are thought to be generated by the collapse of the star's original magnetic field, which becomes highly concentrated as the star shrinks. These extreme magnetic fields play a crucial role in many of the observable phenomena associated with neutron stars. The calm cosmos, in its magnetic embrace, generates fields of immense power. In conclusion, the formation of a neutron star is a dramatic and violent event, the ultimate fate of a massive star that has exhausted its nuclear fuel. What remains is a compact, super-dense, rapidly rotating and highly magnetized object that pushes the boundaries of our understanding of matter and gravity. The calm cosmos, in its extreme conditions, reveals the exotic states of matter, inviting us to explore the profound implications of these cosmic remnants for the nature of reality and our place within its ever-unfolding narrative. One of the most famous manifestations of neutron stars are pulsars. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the neutron star spins, these beams sweep across space, and if one of these beams happens to be pointed towards Earth, we observe regular pulses of radiation, much like a lighthouse. The calm cosmos, in its cosmic lighthouses, guides our gaze across vast distances. The discovery of pulsars in 1967 by Jocelyn Bell Burnell and Anthony Hewish was a monumental moment in astronomy. Initially, the incredibly precise and regular pulses led some to jokingly consider the possibility of little green men, LGM signals. However, it was soon realized that these signals were natural phenomena originating from rapidly rotating neutron stars. The calm cosmos, in its unexpected signals, challenged our assumptions about the universe. Pulsars come in various types, each with unique characteristics. Radio pulsars emit pulses in the radio wavelength and are the most common type. X-ray pulsars are often found in binary systems, where the neutron star accretes matter from a companion star, heating the gas to X-ray emitting temperatures. Millisecond pulsars are a special class that spin at incredibly high rates, sometimes hundreds of times per second, and are thought to have been spun up by accreting matter from a companion star over billions of years. The calm cosmos, in its diverse pulsars, showcases the varied lives of these extreme objects. The extreme regularity of pulsar pulses makes them incredibly precise cosmic clocks, even more accurate than atomic clocks on Earth for certain applications. Astronomers use pulsars for a variety of scientific endeavours, including testing theories of gravity, detecting gravitational waves, and even as navigational beacons for future interstellar travel. The calm cosmos, in its natural precision, provides tools for scientific discovery. Another fascinating type of neutron star is a magnetar. Magnetars are neutron stars with extraordinarily powerful magnetic fields, even stronger than typical neutron stars, trillions of times stronger than Earth's magnetic field. These fields are so intense that they can cause starquakes on the neutron star's surface, releasing enormous bursts of X-rays and gamma rays. The calm cosmos, in its magnetic fury, unleashes bursts of high-energy radiation. Magnetars are responsible for some of the most energetic phenomena observed in the universe, including soft gamma repeaters, SGRS, and anomalous X-ray pulsars, AXPS. SGRs are objects that periodically emit short, intense bursts of gamma rays and X-rays, while AXPs are X-ray pulsars that do not appear to be accreting matter from a companion star, suggesting their X-ray emission is powered by their decaying magnetic fields. The calm cosmos, in its energetic outbursts, reveals the power of extreme magnetic fields. The magnetic fields of magnetars are so strong that they can affect matter in ways we can barely comprehend. They can tear apart atoms, warp space-time, and even affect the vacuum of space itself, creating a highly magnetized plasma. The energy stored in a magnetar's magnetic field is immense, and its sudden release can create a flare that briefly outshines the entire Milky Way galaxy. The calm cosmos, in its magnetic dominance, showcases forces beyond our everyday experience. Neutron stars are not just isolated objects. They often exist in binary systems with other stars. In such systems, the neutron star can accrete matter from its companion, pulling gas from the companion star onto its own surface. This accretion process can lead to powerful X-ray bursts, as the accumulated matter undergoes nuclear fusion on the neutron star's surface. These X-ray bursts are incredibly luminous and provide valuable insights into the behavior of matter under extreme gravitational conditions. The calm cosmos, in its binary dances, reveals the intricate interactions between celestial bodies. When two neutron stars in a binary system orbit each other, they gradually lose energy through the emission of gravitational waves, causing their orbits to shrink. Eventually, they spiral inward and merge in a cataclysmic event known as a kilonova. This merger is a powerful source of gravitational waves, which were first directly detected in 2017 by the LIGO and Virgo observatories from a neutron star merger. The calm cosmos, in its gravitational ripples, allows us to hear the echoes of cosmic collisions. Kilonova events are also thought to be the primary cosmic factories for the production of heavy elements such as gold, platinum, and uranium. The extreme conditions during the merger, including incredibly high temperatures and neutron densities, allow for rapid neutron capture processes that synthesize these elements. This discovery has revolutionized our understanding of the origin of heavy elements in the universe, showing that supernovae are not the only source. The calm cosmos, in its cosmic forge, creates the precious elements that make up our world. In conclusion, neutron stars are not merely the dead remnants of massive stars. They are vibrant, dynamic objects that play a crucial role in the universe. From their precise pulses as pulsars to their energetic outbursts as magnetas, and their role in binary systems and kilonova mergers, these extreme objects continue to challenge and expand our understanding of physics, gravity, and the very fabric of space-time. The calm cosmos, in its extreme conditions, reveals the exotic states of matter and the powerful forces that shape the universe, inviting us to explore the profound implications of these cosmic remnants for the nature of reality and our place within its ever-unfolding narrative. The study of neutron stars is not just about understanding the extreme physics of these objects. It also provides a unique laboratory for testing the fundamental laws of physics under conditions that cannot be replicated on Earth. For instance, the incredible density of neutron stars allows physicists to probe the behavior of matter at densities far exceeding that of atomic nuclei, providing insights into the strong nuclear force and the equation of state of nuclear matter. The calm cosmos, in its cosmic laboratories, offers unparalleled opportunities for scientific discovery. One of the most intriguing aspects of neutron stars is their internal structure. While the outer crust of a neutron star is thought to be a solid lattice of atomic nuclei, the interior is believed to be a superfluid of neutrons, a state of matter where particles can flow without any resistance. Deeper still, the core might contain even more exotic states of matter, such as hyperons, particles containing strange quarks, or even a quark-gluon plasma, where quarks and gluons are no longer confined within individual protons and neutrons. The calm cosmos, in its exotic interiors, harbours mysteries yet to be fully understood. The cooling of neutron stars is another area of active research. Immediately after their formation in a supernova, neutron stars are incredibly hot, with temperatures reaching billions of degrees Kelvin. Over time, they cool down by emitting neutrinos and photons. The rate at which they cool depends on their internal composition and the processes occurring within their core. By observing the temperature of neutron stars at different ages, astronomers can gain insights into their internal structure and the properties of superdense matter. The calm cosmos, in its thermal evolution, reveals the secrets of stellar cooling. Neutron stars also play a crucial role in the evolution of galaxies. Supernovae, which give birth to neutron stars, are responsible for enriching the interstellar medium with heavy elements, which are then incorporated into new generations of stars and planets. The powerful magnetic fields and high-energy radiation emitted by pulsars can also influence the surrounding interstellar gas, creating complex structures and affecting star formation. The calm cosmos, in its galactic cycles, is shaped by the remnants of massive stars. The search for neutron stars continues to be a vibrant field of astronomical research. While many pulsars have been discovered through their radio emissions, the vast majority of neutron stars are likely to be silent, not emitting beams towards Earth. Future observatories, particularly those designed to detect gravitational waves, are expected to uncover many more hidden neutron stars and provide even deeper insights into their nature. The calm cosmos, in its hidden depths, awaits further exploration. One of the most exciting frontiers in neutron star research is the study of their role in gravitational wave astronomy. As mentioned earlier, the merger of two neutron stars is a powerful source of gravitational waves, ripples in space-time that propagate at the speed of light. The direct detection of these waves by LIGO and Virgo has opened up a new window into the universe, allowing us to observe events that are otherwise invisible to traditional electromagnetic telescopes. The calm cosmos, in its gravitational symphony, plays a new tune for us to hear. By studying the gravitational wave signals from neutron star mergers, scientists can extract a wealth of information about these extreme objects. This includes their masses, spins, and even their internal structure. The precise timing of the gravitational wave signal, combined with the electromagnetic light curve from the kilonova, allows for unprecedented insights into the physics of these mergers and the processes that create heavy elements. The calm cosmos, in its multi-messenger astronomy, provides a holistic view of cosmic events. Furthermore, the study of neutron star mergers has provided a new way to measure the expansion rate of the universe, the Hubble constant. By using the gravitational wave signal as a standard siren, an event whose intrinsic luminosity can be determined independently, and combining it with the electromagnetic observations that provide a redshift, a measure of how fast the source is moving away from us, scientists can obtain an independent measurement of the Hubble constant. This offers a valuable cross-check on measurements obtained from other methods, helping to resolve discrepancies and refine our understanding of the universe's expansion. The calm cosmos, in its cosmic measurements, helps us chart the universe's destiny. Beyond mergers, individual neutron stars are also predicted to emit gravitational waves, though these signals are much weaker and have not yet been directly detected. Asymmetric neutron stars, or those with mountains or irregularities on their surface, would continuously emit gravitational waves as they spin. Detecting these continuous gravitational waves would provide unique insights into the internal structure and composition of neutron stars, as well as the properties of nuclear matter at extreme densities. The calm cosmos, in its subtle vibrations, awaits our listening ears. The future of neutron star astronomy is incredibly promising. New and upgraded gravitational wave detectors, along with next-generation X-ray and radio telescopes, will continue to push the boundaries of our understanding. The combination of multi-messenger astronomy, where observations from different cosmic messengers, like gravitational waves and electromagnetic radiation, are combined, will provide an even more complete picture of these extreme objects and the violent events that create them. The calm cosmos, in its boundless mysteries, continues to inspire our scientific endeavours. In conclusion, neutron stars are not just fascinating objects in their own right. They are also invaluable laboratories for testing the fundamental laws of physics and exploring the most extreme conditions in the universe. From their role as cosmic clocks and powerful magnetars, to their involvement in gravitational wave events and the creation of heavy elements, these stellar remnants continue to reveal the profound interconnectedness of the cosmos. The calm cosmos, in its extreme conditions, reveals the exotic states of matter and the powerful forces that shape the universe, inviting us to explore the profound implications of these cosmic remnants for the nature of reality and our place within its ever-unfolding narrative. Let's delve deeper into the fascinating process of a star's death that leads to the birth of a neutron star. The journey begins with a massive star, typically 8 to 20 times the mass of our Sun, reaching the end of its life. Throughout its main sequence phase, such a star burns hydrogen into helium in its core. Once the hydrogen is exhausted, the core contracts and heats up, initiating the fusion of helium into carbon and oxygen. This process continues in successive layers, like an onion, with heavier elements fusing in the hotter, denser core. Each stage of fusion provides the outward pressure needed to counteract the immense inward pull of gravity. The calm cosmos, in its stellar evolution, orchestrates a complex dance of forces. The crucial turning point arrives when the star's core is primarily composed of iron. Iron is unique among the elements because its fusion consumes energy rather than releasing it. This means that once the core becomes iron, it can no longer generate the outward pressure necessary to support the star's immense weight. The delicate balance between gravity and fusion pressure is irrevocably broken. The calm cosmos, in its fundamental laws, dictates the fate of these colossal stars. What follows is a catastrophic gravitational collapse. Within a fraction of a second, the iron core, which is roughly the size of Earth, implodes. The outer layers of the star, still undergoing fusion, fall inward at incredible speeds, reaching up to 70,000 kilometers per second, or about 23% of the speed of light. This inward rush of matter compresses the core to an unimaginable density. The calm cosmos, in its cosmic implosions, demonstrates the overwhelming power of gravity. As the core collapses, the protons and electrons are squeezed together with such force that they overcome their electrostatic repulsion and combine to form neutrons and neutrinos. This process, known as electron capture or inverse beta decay, is a key step in the formation of a neutron star. The neutrinos, being weakly interacting particles, escape almost immediately, carrying away a tremendous amount of energy, about 99% of the energy released in a supernova. This neutrino burst is so powerful that it can briefly make the star shine brighter in neutrinos than in visible light. The calm cosmos, in its subatomic transformations, reveals the hidden energies of the universe. The remaining neutrons are then packed together incredibly tightly, forming a degenerate neutron gas. This gas resists further compression due to the Pauli exclusion principle, which states that no two identical fermions, like neutrons, can occupy the same quantum state. This resistance creates an outward pressure known as neutron degeneracy pressure, which is strong enough to halt the collapse of the core, provided the core's mass is within a certain limit, the Tolman-Oppenheimer-Volkoff limit, which is around 2 to 3 solar masses. If the core's mass exceeds this limit, even neutron degeneracy pressure cannot withstand the gravity, and the core will continue to collapse, forming a black hole. The calm cosmos, in its quantum mechanics, sets the ultimate limits of stellar remnants. Upon reaching nuclear densities, the collapsing core essentially bounces back, creating a powerful shock wave that propagates outward through the infalling stellar material. This shock wave, combined with the immense energy deposited by the escaping neutrinos, is what ultimately drives the supernova explosion. The outer layers of the star are violently ejected into space, enriching the interstellar medium with newly synthesized heavy elements. This material will eventually become the raw ingredients for future generations of stars, planets, and even life itself. The calm cosmos, in its cycle of life and death, ensures the continuous creation of cosmic ingredients. So, the supernova is not just a spectacular light show, it is the cosmic mechanism by which the elements heavier than iron, forged in the heart of the dying star, are dispersed throughout the galaxy. Without supernovae, the universe would be a much simpler place, devoid of the complex chemistry necessary for the formation of rocky planets and biological life. The calm cosmos, in its explosive artistry, paints the universe with the colours of creation. The newly formed neutron star born from this violent crucible is an object of truly extreme properties. Its density is mind-boggling. Imagine compressing Mount Everest into a sugar cube. That's still not dense enough. A neutron star is so dense that a thimbleful of its material would weigh more than all the people on Earth combined. This extreme density means that the atoms as we know them cease to exist. Instead, it's a sea of neutrons, with a small percentage of protons and electrons. The calm cosmos, in its ultimate compression, transforms matter into its most fundamental state. The surface of a neutron star is also incredibly smooth, with irregularities no more than a few millimeters high, despite its immense gravity. This is because the gravitational forces are so strong that they would crush any significant mountains or valleys. The calm cosmos, in its gravitational perfection, creates a surface of unparalleled smoothness. Furthermore, the magnetic fields of neutron stars are among the strongest in the universe. As the star's original magnetic field lines are compressed during the collapse, they become incredibly concentrated, leading to field strengths billions to trillions of times stronger than Earth's. These powerful magnetic fields are responsible for many of the observable phenomena associated with neutron stars, including their emission of radiation as pulsars and the energetic outbursts of magnetars. The calm cosmos, in its magnetic embrace, generates fields of immense power. In conclusion, the formation of a neutron star is a testament to the extreme forces at play in the universe. It is a process of gravitational collapse, nuclear transformation, and explosive ejection that leaves behind one of the most fascinating and enigmatic objects in the cosmos. The calm cosmos, in its grand cosmic drama, reveals the profound interconnectedness of stellar life cycles and the continuous creation of the universe's building blocks. It is a reminder that the death of one star can be the spectacular birth of another, and that even in destruction, there is creation. Let's now explore the various types of neutron stars and the unique phenomena associated with them, beyond just pulsars and magnetars. The diversity of these compact objects highlights the rich tapestry of extreme physics at play in the universe. The calm cosmos, in its varied remnants, showcases the myriad ways stars can end their lives. Beyond the well-known radio pulsars, there are also X-ray pulsars, which are often found in binary systems. In these systems, a neutron star orbits a normal companion star, and its immense gravity pulls matter from the companion. This matter forms an accretion disk around the neutron star, spiraling inward and heating up to millions of degrees Celsius, emitting copious amounts of X-rays. As the neutron star rotates, its magnetic field channels this accreting matter onto its magnetic poles, creating hotspots that sweep across our line of sight, resulting in regular X-ray pulses. These X-ray pulses provide invaluable insights into accretion processes and the behavior of matter in extreme gravitational fields. The calm cosmos, in its binary dances, reveals the intricate interactions between celestial bodies. Another fascinating class of neutron stars are recycled pulsars, or millisecond pulsars. These are neutron stars that have been spun up to incredibly high rotation rates, sometimes hundreds of times per second, by accreting matter and angular momentum from a companion star over billions of years. This process effectively recycles an old, slowly spinning neutron star into a rapidly rotating one. Millisecond pulsars are among the most stable and precise clocks in the universe, even more accurate than atomic clocks on Earth over long periods. Their extreme precision makes them ideal tools for testing theories of gravity, detecting gravitational waves, and even for future deep space navigation. The calm cosmos, in its cosmic precision, provides natural laboratories for fundamental physics. Some neutron stars are observed to be isolated neutron stars, meaning they are not part of a binary system and do not exhibit pulsar activity. These are often difficult to detect, as they are faint and only emit thermal radiation from their cooling surfaces. However, their study is crucial for understanding the cooling mechanisms of neutron stars and the properties of their exotic interiors. The calm cosmos, in its solitary wanderers, hides secrets within its depths. Then there are central compact objects, CCOS, which are neutron stars found at the centers of supernova remnants. Unlike typical pulsars, CCOs do not show strong pulsed emission, and their magnetic fields appear to be much weaker than those of pulsars or magnetars. Their exact nature and evolutionary pathway are still subjects of active research, but they represent another distinct population of neutron stars that challenge our understanding of stellar evolution and magnetic field generation. The calm cosmos, in its diverse remnants, continues to surprise us with new discoveries. Beyond these classifications, the study of neutron stars also involves understanding their interactions with their surroundings. For instance, some neutron stars are observed to have fallback disks, remnants of the supernova explosion that didn't quite escape the neutron star's gravitational pull and instead formed a disk of material around it. These disks can accrete onto the neutron star over long timescales, potentially influencing its spin and magnetic field evolution. The calm cosmos, in its cosmic aftermath, reveals the lingering effects of stellar death. The surfaces of neutron stars are also incredibly interesting. While often described as smooth, they can have mountains, tiny deformations caused by the immense gravitational forces and the internal structure of the star. These mountains, though only a few millimeters high, are significant because they could be a source of continuous gravitational waves, which next-generation gravitational wave detectors might be able to detect. The calm cosmos, in its subtle imperfections, might reveal new gravitational wave signals. Furthermore, the extreme magnetic fields of some neutron stars, particularly magnetars, can lead to phenomena like starquakes. These are sudden rearrangements of the neutron star's crust, caused by the immense stresses exerted by the magnetic field. Starquakes can release enormous amounts of energy in the form of X-ray and gamma-ray flares, making magnetars some of the most luminous objects in the high-energy sky. The calm cosmos, in its magnetic fury, unleashes bursts of high-energy radiation. The study of neutron stars also extends to their role in the broader cosmic environment. They are not just isolated objects, but are intricately linked to the cycle of matter and energy in galaxies. Supernovae, which produce neutron stars, are crucial for dispersing heavy elements throughout the interstellar medium, enriching the gas clouds from which new stars and planets form. Without these cosmic explosions, the universe would be a much less chemically diverse place, and the formation of rocky planets, and life as we know it, would be impossible. The calm cosmos, in its grand cycle, ensures the continuous creation of cosmic ingredients. In conclusion, the diverse population of neutron stars, from their various emission mechanisms to their unique physical properties and interactions, provides a rich laboratory for exploring the most extreme conditions in the universe. Each type of neutron star offers a unique window into the fundamental laws of physics, the behavior of matter at unimaginable densities, and the intricate processes of stellar evolution. The calm cosmos, in its varied remnants, continues to challenge and expand our understanding of the universe, inviting us to explore the profound implications of these cosmic wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now delve into the exotic internal structure of neutron stars, a realm where matter exists in states unlike anything we encounter on Earth. Understanding the interior of these super-dense objects is crucial for unlocking the secrets of nuclear physics and the fundamental forces that govern the universe. The calm cosmos, in its extreme conditions, provides a unique laboratory for probing the very limits of matter. Imagine peeling back the layers of a neutron star, much like an onion. The outermost layer, the atmosphere, is incredibly thin, perhaps only a few centimeters thick, and consists of a plasma of electrons and ions. Below this, we find the outer crust, a solid lattice of heavy atomic nuclei like iron, and a sea of relativistic electrons. This crust is incredibly rigid, billions of times stronger than steel, due to the immense gravitational pressure. The calm cosmos, in its crushing embrace, creates materials of unimaginable strength. As we go deeper, the density increases dramatically. In the inner crust, the pressure becomes so intense that neutrons begin to drip out of the nuclei, forming a superfluid of free neutrons coexisting with the nuclei and electrons. This region is often described as a nuclear pasta phase, where the nuclei can take on strange and complex shapes, like spaghetti, lasagna, or gnocchi, due to the competing forces of nuclear attraction and Coulomb repulsion. The calm cosmos, in its subatomic cuisine, serves up exotic forms of matter. Below the inner crust lies the outer core, which is thought to be composed primarily of a superfluid of neutrons, along with a small percentage of superconducting protons and normal electrons. A superfluid is a state of matter that behaves like a fluid with zero viscosity, meaning it can flow without any resistance. This exotic state is possible due to the extreme cold temperatures within the neutron star, despite its initial fiery birth. The calm cosmos, in its paradoxical conditions, allows for frictionless flow. And finally, at the very heart of the neutron star lies the inner core, the most mysterious and extreme region. Here, the densities are so immense, several times that of an atomic nucleus, that our current understanding of physics begins to break down. Various theoretical models propose different compositions for the inner core. It could be a mixture of exotic particles like hyperons, particles containing strange quarks, or it could be a deconfined quark-gluon plasma, where the quarks and gluons that normally make up protons and neutrons are no longer confined and can move freely. The calm cosmos, in its deepest secrets, holds the ultimate mysteries of matter. Another possibility for the inner core is the existence of strange quark matter, or strange stars. This hypothetical state of matter is even more stable than ordinary nuclear matter and would consist of up, down, and strange quarks. If strange quark matter exists, then some neutron stars might actually be strange stars, composed entirely of this exotic material. The calm cosmos, in its theoretical possibilities, expands our understanding of fundamental particles. Understanding the precise composition of the neutron star interior is one of the holy grails of nuclear astrophysics. It requires bridging the gap between nuclear physics, which describes the interactions of particles at subatomic scales, and astrophysics, which deals with the behavior of matter under extreme gravitational conditions. Observations of neutron stars, such as their masses, radii, and cooling rates, provide crucial constraints for theoretical models of their internal structure. The calm cosmos, in its cosmic laboratories, allows us to test the limits of our physical theories. For example, precise measurements of neutron star radii can help distinguish between different equations of state for nuclear matter. A stiffer equation of state where matter is more resistant to compression would result in larger neutron stars for a given mass, while a softer equation of state would lead to smaller radii. The calm cosmos, in its subtle variations, provides clues to its fundamental nature. Furthermore, the study of neutron star cooling rates can provide insights into the presence of exotic particles or phases of matter in their cores. The presence of certain particles, like hyperons or quarks, can significantly enhance the cooling rate of a neutron star through various neutrino emission processes. By comparing theoretical cooling curves with observational data, scientists can infer the composition of the neutron star interior. The calm cosmos, in its thermal signatures, reveals its hidden components. In conclusion, the internal structure of neutron stars is a fascinating and complex frontier in astrophysics and nuclear physics. From their rigid crusts to their superfluid interiors and potentially exotic cores, these objects are unique laboratories for exploring the behavior of matter under the most extreme conditions imaginable. The calm cosmos, in its exotic interiors, harbours mysteries yet to be fully understood, inviting us to push the boundaries of our knowledge and unravel the fundamental nature of matter and the forces that govern the universe. It is a reminder that the more we learn about the universe, the more we realize how much more there is to discover and how deeply interconnected we are with the fundamental fabric of reality. Let's now explore the profound role that neutron stars play in the grand cosmic scheme, extending beyond their individual properties to their influence on the evolution of galaxies and the distribution of elements in the universe. These compact remnants are not merely end products of stellar evolution. They are active participants in the ongoing cosmic cycle of creation and destruction. The calm cosmos, in its intricate dance of matter and energy, reveals the far-reaching impact of these extreme objects. One of the most significant contributions of neutron stars to galactic evolution comes indirectly through the supernova explosions that create them. As we discussed, Type II supernovae are responsible for dispersing vast quantities of heavy elements forged in the star's core during its life and death into the interstellar medium. These elements, including carbon, oxygen, silicon, and iron, are essential building blocks for subsequent generations of stars, planets, and ultimately life itself. Without these cosmic explosions, the universe would be a much simpler, less chemically diverse place. The calm cosmos, in its explosive artistry, enriches the galactic canvas. Beyond the initial dispersal, neutron stars, particularly pulsars, can also influence their surroundings through their powerful winds and high-energy emissions. Pulsars emit relativistic winds of charged particles that can create vast nebulae, known as pulsar wind nebulae, which glow brightly in X-rays and gamma rays. These nebulae can interact with the surrounding interstellar gas, heating it and potentially triggering or inhibiting star formation in nearby regions. The calm cosmos, in its energetic outflows, sculpts the interstellar landscape. Furthermore, the extreme magnetic fields of magnetars can have a significant impact on the interstellar medium. The sudden, powerful bursts of X-rays and gamma rays from magnetars can ionize large regions of gas, creating transient changes in the chemical and physical properties of the interstellar environment. While localized, these events contribute to the overall dynamic nature of galactic ecosystems. The calm cosmos, in its magnetic storms, stirs the galactic pot. Neutron stars also play a crucial role in the formation of binary systems and the subsequent evolution of those systems. Many neutron stars are found in binary pairs with other stars, and the gravitational interactions within these systems can lead to a variety of phenomena, including X-ray binaries, where matter accretes onto the neutron star, and millisecond pulsars, which are spun up by this accretion. These binary systems are important sources of gravitational waves and X-ray emission, providing unique insights into the dynamics of compact objects. The calm cosmos, in its gravitational embraces, orchestrates cosmic partnerships. The most dramatic and far-reaching impact of neutron stars on the universe's chemical evolution comes from the merger of two neutron stars, a phenomenon known as a kilonova. These mergers, now directly observed through gravitational waves and electromagnetic radiation, are thought to be the primary cosmic factories for the production of the heaviest elements in the universe, elements beyond iron that cannot be formed in supernovae. This includes precious metals like gold and platinum, as well as radioactive elements like uranium. The calm cosmos, in its cosmic forge, creates the rarest treasures of the universe. During a kilonova, the extreme conditions of the merger, incredibly high temperatures, densities, and neutron fluxes, allow for a process called rapid neutron capture, or the R process. In this process, atomic nuclei rapidly absorb a large number of neutrons before they have a chance to decay, building up to very heavy unstable isotopes. These isotopes then undergo radioactive decay, forming the stable heavy elements we observe. This discovery has fundamentally changed our understanding of where the heaviest elements come from, showing that supernovae alone cannot account for their abundance. The calm cosmos, in its violent unions, seeds the universe with its most precious elements. The material ejected from kilonova mergers, rich in these heavy elements, is then dispersed into the interstellar medium, where it mixes with gas and dust, and eventually becomes incorporated into new stars and planetary systems. This means that the gold in your jewellery, the uranium in nuclear reactors, and many other heavy elements on Earth were likely forged in the fiery collision of two neutron stars billions of years ago, long before our solar system even existed. The calm cosmos, in its cosmic recycling, ensures the continuous enrichment of its matter. In essence, neutron stars are not just cosmic curiosities, they are integral components of the universe's grand evolutionary narrative, from seeding galaxies with life-essential elements to influencing star formation and creating the heaviest elements. Their existence and interactions profoundly shape the cosmos we inhabit. The calm cosmos, in its intricate web of cause and effect, demonstrates how the most extreme events can lead to the most profound and beautiful outcomes. It is a reminder that the more we learn about the universe, the more we realize how much more there is to discover and how deeply interconnected we are with the fundamental fabric of reality. Let's now explore the cutting-edge observational techniques and future prospects in the study of neutron stars. Our understanding of these enigmatic objects has been revolutionized by advancements in astronomy, and new technologies promise even deeper insights into their extreme physics. The calm cosmos, in its vastness, continuously reveals its secrets through the ingenuity of human observation. Historically, the primary way we detected neutron stars was through their pulsed radio emission as pulsars. Radio telescopes like the Arecibo Observatory, before its collapse, and the Green Bank Telescope have been instrumental in discovering thousands of pulsars, mapping their distribution in the Milky Way and precisely measuring their properties. The extreme regularity of pulsar pulses allows for incredibly precise timing experiments, which have been used to detect exoplanets, study the interstellar medium, and even test Einstein's theory of general relativity and strong gravitational fields. The calm cosmos, in its radio whispers, guides our scientific endeavours. However, not all neutron stars are pulsars, and many do not emit in the radio band. X-ray astronomy has opened another crucial window into the neutron star population. X-ray telescopes, such as NASA's Chandra X-ray Observatory and ESA's XMM Newton, are essential for studying X-ray pulsars in binary systems, magnetars during their energetic outbursts, and cooling isolated neutron stars. The high-energy emission from these objects provides unique information about their surface temperatures, magnetic fields, and accretion processes. The calm cosmos, in its X-ray glow, reveals the hot and energetic lives of neutron stars. Gamma-ray astronomy, particularly with instruments like the Fermi Gamma Ray Space Telescope, has also contributed significantly to our understanding of neutron stars. Many pulsars are found to emit gamma rays, and magnetars are the most powerful sources of gamma ray bursts. Studying these high-energy emissions helps us understand the particle acceleration mechanisms and the extreme magnetic environments around neutron stars. The calm cosmos, in its gamma-ray flashes, illuminates the most violent events. But perhaps the most revolutionary development in neutron star astronomy has been the advent of gravitational wave astronomy. The direct detection of gravitational waves in 2015 by the LIGO collaboration, and especially the detection of gravitational waves from a binary neutron star merger, GW 170817, in 2017, has opened an entirely new way to observe these objects. Gravitational waves are ripples in space-time itself, generated by the acceleration of massive objects, and neutron star mergers are among the most powerful sources. The calm cosmos, in its gravitational symphony, plays a new tune for us to hear. Multi-messenger astronomy, the coordinated observation of cosmic events using different types of messengers, electromagnetic waves, gravitational waves, neutrinos, cosmic rays, is now the frontier of astrophysics. The observation of GW 170817 was a landmark event, as it was the first time a cosmic event was observed in both gravitational waves and electromagnetic radiation. This allowed astronomers to pinpoint the location of the merger, study the kilonova, and confirm that neutron star mergers are indeed the cosmic factories for heavy elements. The calm cosmos, in its multi-messenger symphony, provides a holistic view of cosmic events. Looking to the future, several exciting developments are on the horizon. Next-generation gravitational wave detectors, such as the Cosmic Explorer and the Einstein telescope, will be significantly more sensitive than current instruments, allowing us to detect neutron star mergers from much greater distances and with higher precision. These observatories will provide a much larger sample of merger events, enabling more robust statistical studies and deeper insights into the equation of state of nuclear matter. The calm cosmos, in its gravitational ripples, awaits our enhanced listening. New X-ray observatories, like the Athena X-ray Observatory, will offer unprecedented sensitivity and resolution, allowing us to study the surfaces and atmospheres of neutron stars in greater detail, and to probe the physics of accretion onto these compact objects. Radio astronomy is also undergoing a renaissance with the development of large arrays like the Square Kilometre Array, SKA, which will be able to detect fainter and more distant pulsars, and potentially discover new types of neutron stars. The calm cosmos, in its diverse emissions, promises new revelations. Furthermore, the development of neutrino telescopes like IceCube is opening up the possibility of detecting neutrinos from supernovae and neutron star mergers. While challenging, a neutrino detection from a supernova would provide invaluable information about the core collapse process, which is currently hidden from electromagnetic observation. The calm cosmos, in its elusive particles, offers another window into extreme cosmic events. Beyond observations, theoretical and computational astrophysics continue to play a vital role in understanding neutron stars. Supercomputer simulations are used to model the complex processes of supernova explosions, neutron star formation, and binary neutron star mergers, providing crucial predictions that can be tested against observational data. These simulations help us interpret the signals we receive and push the boundaries of our theoretical understanding. The calm cosmos, in its computational models, allows us to recreate its most violent phenomena. In conclusion, the study of neutron stars is a dynamic and rapidly evolving field, driven by continuous advancements in observational techniques and theoretical modeling. From radio and X-ray observations to the revolutionary insights from gravitational wave astronomy, our understanding of these extreme objects is constantly expanding. The calm cosmos, in its vastness, continuously reveals its secrets through the ingenuity of human observation, inviting us to explore the profound implications of these cosmic wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now delve into the fascinating and often counterintuitive physics that governs neutron stars, exploring concepts like the equation of state, superfluidity, and superconductivity in their extreme environments. These phenomena are not just theoretical curiosities, they have profound implications for understanding the fundamental nature of matter and the forces that bind it. The calm cosmos in its most extreme laboratories allows us to test the very limits of our physical theories. The equation of state, EOS, of nuclear matter is perhaps the most crucial and least understood aspect of neutron star physics. The EOS describes the relationship between pressure and density within the neutron star, and it dictates the star's internal structure, its maximum possible mass, and its radius. At the extreme densities found in neutron stars, matter behaves in ways that cannot be replicated in terrestrial laboratories. The strong nuclear force, which binds protons and neutrons together in atomic nuclei, plays a dominant role, but its behavior at these densities is still not fully understood. The calm cosmos, in its ultimate compression, challenges our understanding of fundamental forces. Different theoretical models for the EOS predict different properties for neutron stars. For example, a stiff EOS, where matter is very resistant to compression, would result in larger neutron stars for a given mass. Conversely, a soft EOS, where matter is more compressible, would lead to smaller radii. By precisely measuring the masses and radii of neutron stars through astronomical observations, scientists can constrain the EOS and gain insights into the behavior of nuclear matter at supernuclear densities. The calm cosmos, in its subtle variations, provides clues to its fundamental nature. One of the most intriguing predictions for the interior of neutron stars is the existence of superfluidity and superconductivity. Superfluidity is a state of matter where a fluid flows without any viscosity or friction. Superconductivity is a state where electric current flows without any resistance. These phenomena typically occur at extremely low temperatures on Earth, but in neutron stars they are predicted to occur at much higher temperatures due to the incredibly high densities. The calm cosmos, in its paradoxical conditions, allows for frictionless flow and resistance-free currents. In the inner crust of a neutron star, the free neutrons are expected to form a superfluid. This means that they can flow without any resistance, and their motion is not impeded by the surrounding atomic nuclei. This superfluidity has observable consequences such as glitches in pulsar rotation. Pulsars are incredibly stable rotators, but occasionally they experience sudden small increases in their spin rate, known as glitches. These glitches are thought to be caused by the sudden transfer of angular momentum from the rapidly rotating superfluid interior to the solid outer crust. The calm cosmos, in its cosmic gyroscopes, reveals the subtle effects of superfluidity. Below the inner crust in the outer core, the protons are predicted to become superconducting. This means that they can carry electric currents without any resistance. This superconductivity is crucial for understanding the incredibly strong magnetic fields of neutron stars. If the protons were not superconducting, the magnetic field would decay much faster than observed. The calm cosmos, in its magnetic embrace, relies on the exotic properties of matter. The presence of superfluidity and superconductivity in neutron stars has profound implications for their cooling and evolution. Superfluid neutrons can carry heat more efficiently than normal matter, affecting the cooling rate of the star. Superconducting protons can trap magnetic flux lines, influencing the magnetic field evolution. By studying the cooling curves of neutron stars and the decay of their magnetic fields, astronomers can infer the presence and properties of these exotic states of matter. The calm cosmos, in its thermal and magnetic signatures, reveals its hidden components. Beyond superfluidity and superconductivity, the inner core of a neutron star might harbour even more exotic states of matter. As mentioned earlier, possibilities include hyperons, which are baryons containing strange quarks, or even a deconfined quark-gluon plasma, where the quarks and gluons are no longer confined within individual protons and neutrons. The existence of these exotic phases would significantly affect the EOS and the observable properties of neutron stars. The calm cosmos, in its deepest secrets, holds the ultimate mysteries of matter. The study of these exotic states of matter in neutron stars is a truly interdisciplinary endeavour, bridging nuclear physics, condensed matter physics, and astrophysics. It requires sophisticated theoretical calculations, numerical simulations, and precise astronomical observations. The calm cosmos, in its cosmic laboratories, allows us to test the limits of our physical theories and push the boundaries of our understanding of the fundamental building blocks of the universe. In conclusion, the physics of neutron stars is a rich and complex field, revealing the extraordinary behavior of matter under the most extreme conditions imaginable. From the elusive equation of state to the fascinating phenomena of superfluidity and superconductivity, these objects are unique laboratories for exploring the fundamental forces and particles that govern our universe. The calm cosmos, in its extreme conditions, continues to challenge and expand our understanding of matter, inviting us to explore the profound implications of these cosmic wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now explore the profound connection between neutron stars and the burgeoning field of gravitational wave astronomy. The direct detection of gravitational waves has opened an entirely new window into the universe, allowing us to observe events that are otherwise invisible to traditional electromagnetic telescopes. Neutron star mergers, in particular, have emerged as crucial sources for these cosmic ripples, providing unprecedented insights into the most extreme phenomena in the cosmos. The calm cosmos, in its gravitational symphony, plays a new tune for us to hear. Gravitational waves are ripples in the fabric of space-time, predicted by Albert Einstein's theory of general relativity. They are generated by the acceleration of massive objects, and the more massive and rapidly accelerating the objects, the stronger the gravitational waves they produce. While many cosmic events generate gravitational waves, the inspiral and merger of compact objects, black holes and neutron stars, are among the most powerful sources detectable by current observatories. The calm cosmos, in its cosmic dances, creates ripples that traverse the universe. The landmark event that truly revolutionized our understanding of neutron stars and gravitational waves was the detection of GW 170817 in August 2017. This signal was not just a gravitational wave detection, it was the first time a cosmic event was observed in both gravitational waves and electromagnetic radiation. The gravitational wave signal, detected by the LIGO and Virgo observatories, indicated the merger of two neutron stars. Just 1.7 seconds later, a burst of gamma rays was detected by the Fermi Gamma Ray Space Telescope, followed by a kilonova, an electromagnetic transient observed across the entire spectrum from X-rays to radio waves. The calm cosmos, in its multi-messenger symphony, provided a holistic view of a cosmic cataclysm. This multi-messenger observation of GW 170817 provided a wealth of information. Firstly, it confirmed that binary neutron star mergers are indeed the progenitors of short gamma-ray bursts, solving a long-standing mystery in astrophysics. Secondly, the kilonova emission, rich in heavy elements, provided direct evidence that these mergers are the primary cosmic factories for the production of elements heavier than iron, such as gold, platinum, and uranium, through the rapid neutron capture process, R process. This discovery fundamentally changed our understanding of the origin of these elements in the universe. The calm cosmos, in its cosmic forge, creates the rarest treasures of the universe. Furthermore, the combined gravitational wave and electromagnetic observations of GW 170817 allowed for an independent measurement of the Hubble constant, the rate at which the universe is expanding. By using the gravitational wave signal as a standard siren, an event whose intrinsic luminosity can be determined independently, and combining it with the electromagnetic observations that provide a redshift, a measure of how fast a source is moving away from us, scientists obtained a new, independent measurement of the Hubble constant. This offers a valuable cross-check on measurements obtained from other methods, helping to resolve discrepancies and refine our understanding of the universe's expansion. The calm cosmos, in its cosmic measurements, helps us chart the universe's destiny. Beyond mergers, individual neutron stars are also predicted to emit gravitational waves, though these signals are much weaker and have not yet been directly detected. Asymmetric neutron stars, or those with mountains or irregularities on their surface, would continuously emit gravitational waves as they spin. Detecting these continuous gravitational waves would provide unique insights into the internal structure and composition of neutron stars, as well as the properties of nuclear matter at extreme densities. The calm cosmos, in its subtle vibrations, awaits our listening ears. The future of neutron star astronomy, particularly with gravitational waves, is incredibly promising. Next-generation gravitational wave detectors, such as the Cosmic Explorer and the Einstein telescope, will be significantly more sensitive than current instruments, allowing us to detect neutron star mergers from much greater distances and with higher precision. These observatories will provide a much larger sample of merger events, enabling more robust statistical studies and deeper insights into the equation of state of nuclear matter. The calm cosmos, in its gravitational ripples, awaits our enhanced listening. Moreover, the development of space-based gravitational wave observatories, like LISA, Laser Interferometer Space Antenna, will open up the low-frequency gravitational wave spectrum, allowing us to detect the spiral of supermassive black holes and potentially other exotic sources. While not directly observing neutron stars, these missions will complement ground-based detectors and provide a more complete picture of the gravitational wave universe. The calm cosmos, in its vastness, promises new revelations through the lens of gravitational waves. In conclusion, neutron stars are at the forefront of gravitational wave astronomy, serving as crucial laboratories for testing the fundamental laws of physics and understanding the most extreme phenomena in the universe. The multi-messenger observation of GW 17/0817 marked a new era in astrophysics, demonstrating the power of combining different cosmic messengers to unravel the universe's mysteries. The calm cosmos, in its gravitational symphony, continues to reveal its profound secrets, inviting us to explore the nature of reality and our place within its ever-unfolding narrative. Let's now consider the intriguing, albeit highly speculative question of whether neutron stars could somehow be involved in, or even host exotic forms of life. While the conditions on and around neutron stars are unimaginably extreme, pushing the boundaries of what we consider habitable, the vastness and strangeness of the cosmos often challenge our anthropocentric assumptions about life. The calm cosmos, in its boundless diversity, might harbour life in forms we can barely conceive. Our conventional understanding of life, as we know it on Earth, requires liquid water, a stable energy source, and a relatively benign environment with moderate temperatures and pressures. Neutron stars, with their crushing gravity, extreme temperatures, initially, intense radiation, and powerful magnetic fields, seem to be the antithesis of a habitable environment. The surface gravity is so strong that a human would be instantly flattened to a thin film, and the radiation would sterilize anything organic. The calm cosmos, in its harsh realities, presents environments seemingly hostile to life. However, the concept of exotic life extends beyond our carbon-based water-dependent paradigm. Scientists and astrobiologists have speculated about life forms that could exist in environments vastly different from Earth. For instance, some theories propose life based on silicon instead of carbon, or life that thrives in liquid methane or ammonia instead of water. But even these alternative chemistries would struggle to survive the sheer extremes of a neutron star. The calm cosmos, in its theoretical possibilities, pushes the boundaries of biological imagination. One highly speculative idea involves the possibility of nuclear life within the core of a neutron star. This concept, often bordering on science fiction, suggests that under the immense pressures and densities, complex structures could form from nuclear matter, perhaps exhibiting self-organization and replication. However, there is currently no scientific evidence or theoretical framework to support such a notion, and the timescales for such processes would likely be incredibly short due to the rapid cooling and dynamic nature of the neutron star interior. The calm cosmos, in its deepest mysteries, remains silent on the existence of nuclear life. A more plausible, though still extremely speculative, scenario might involve the very distant future of neutron stars. As neutron stars cool over billions and trillions of years, their surface temperatures would eventually drop to a point where some form of exotic chemistry might become possible on their surfaces, assuming some form of atmosphere could be retained. However, even then, the immense gravity and radiation would pose formidable challenges. The calm cosmos, in its distant future, might witness new forms of existence. Perhaps the most intriguing and slightly less fantastical connection between neutron stars and life lies not in the neutron stars themselves, but in the events that create them and the elements they forge. As we discussed, supernovae and neutron star mergers are the primary cosmic factories for the production of heavy elements, including those essential for life as we know it, such as carbon, oxygen, and especially the heavy metals like iron, which is crucial for hemoglobin in our blood, and gold and platinum, which are formed in kilonovae. Without these cataclysmic events, the raw ingredients for planets and life would not exist in the abundance we observe. The calm cosmos, in its violent creation, provides the building blocks of life. In this sense, neutron stars are indirectly vital for life. Their violent birth and subsequent mergers are part of the grand cosmic cycle that enriches the universe with the necessary elements for complex chemistry and biological evolution. So, while a neutron star itself is an unlikely abode for life, the processes that lead to its formation and the events it participates in are fundamental to the existence of life elsewhere in the cosmos. The calm cosmos, in its intricate web of cause and effect, demonstrates the profound interconnectedness of all cosmic phenomena. Furthermore, the extreme conditions around neutron stars, particularly the powerful magnetic fields and intense radiation, could potentially be harnessed by incredibly advanced civilizations. While this is pure speculation, some science fiction concepts explore the idea of civilizations living near, or even on neutron stars, utilizing their immense energy output or unique physical properties. However, such concepts are far beyond our current understanding of physics and engineering. The calm cosmos, in its theoretical frontiers, invites us to imagine the unimaginable. In conclusion, while the direct existence of life on or within neutron stars remains firmly in the realm of science fiction and extreme speculation, these enigmatic objects play an undeniable, albeit indirect, role in the cosmic story of life. Their formation and mergers are crucial for the creation and dispersal of the heavy elements that are the very building blocks of planets and biological organisms. The calm cosmos, in its boundless diversity, might harbour life in forms we can barely conceive, but it is through the violent deaths of massive stars that the seeds of life are sown across the universe. It is a reminder that the more we learn about the universe, the more we realise how much more there is to discover, and how deeply interconnected we are with the fundamental fabric of reality. Let's now turn our attention to the fascinating history of how neutron stars were first theorised and subsequently discovered, a journey that spans decades of scientific inquiry and technological innovation. The calm cosmos, in its slow unveiling, rewards persistent observation and theoretical foresight. The concept of neutron stars emerged from theoretical physics long before their observational confirmation. In 1932, just a year after the discovery of the neutron by James Chadwick, Lev Landau, a Soviet physicist, theorized the existence of super-dense stars composed entirely of neutrons. He reasoned that if a star's core collapsed beyond the white dwarf stage, where electron degeneracy pressure supports it, the electrons would be forced into the protons, forming neutrons, and these neutrons would then provide a new form of degeneracy pressure to resist further collapse. The calm cosmos, in its theoretical elegance, hinted at the existence of these exotic objects. Building on this, in 1934, Walter Bairdi and Fritz Zwicky, two astronomers working at Caltech, proposed that supernovae were the transition from normal stars to neutron stars. They correctly predicted that these explosions would release enormous amounts of energy and produce these incredibly dense remnants. Their foresight was remarkable, considering the limited observational data available at the time. The calm cosmos, in its dramatic events, was theorized to give birth to these compact objects. However, these theoretical predictions remained largely speculative for decades, as there was no observational evidence to support the existence of such extreme objects. The technology to detect them simply didn't exist. The calm cosmos, in its vastness, kept its secrets well. The breakthrough came in 1967 with the accidental discovery of pulsars by Jocelyn Bell Burnell, a graduate student, and her supervisor Anthony Hewish at the University of Cambridge. They detected incredibly regular radio pulses coming from a specific point in the sky, initially dubbed LGM-1 for Little Green Men, due to their astonishing regularity. The pulses were so precise that they initially considered an extraterrestrial origin. The calm cosmos, in its unexpected signals, challenged our assumptions. It was soon realized that these signals were not from aliens, but from rapidly rotating neutron stars. As the neutron star spins, its magnetic field sweeps a beam of radio waves across space, much like a lighthouse. If this beam crosses Earth, we detect a pulse. This model perfectly explained the extreme regularity of the signals and provided the first observational evidence for the existence of neutron stars, nearly 35 years after their theoretical prediction. The calm cosmos, in its cosmic lighthouses, revealed its hidden wonders. Following the discovery of pulsars, the field of neutron star astronomy exploded. More and more pulsars were discovered and their properties were meticulously studied. This led to the identification of different types of pulsars, including millisecond pulsars, X-ray pulsars, and eventually magnetars, each revealing new facets of these extreme objects. The calm cosmos, in its diverse manifestations, continued to surprise and enlighten us. Further confirmation of neutron stars came from observations of supernova remnants. The Crab Nebula, the remnant of a supernova observed in 1054 AD, was found to contain a pulsar at its centre, providing a direct link between supernovae and neutron stars. This observation solidified the Baird and Zwicky hypothesis. The calm cosmos, in its historical records, confirmed the predictions of its theorists. The advent of X-ray and gamma-ray astronomy in the latter half of the 20th century provided even more insights. X-ray telescopes allowed us to study accreting neutron stars in binary systems, revealing the intense heat generated by matter falling onto their surfaces. Gamma-ray observatories detected the powerful bursts from magnetars, confirming the existence of neutron stars with incredibly strong magnetic fields. The calm cosmos, in its high-energy emissions, unveiled the most violent aspects of neutron stars, and most recently, the direct detection of gravitational waves from a binary neutron star merger in 2017 marked another monumental milestone. This event, GW 170817, not only confirmed the existence of binary neutron star systems, but also provided unprecedented insights into their mergers and their role in producing heavy elements. It opened up the era of multi-messenger astronomy, allowing us to study cosmic events through both gravitational waves and electromagnetic radiation. The calm cosmos, in its gravitational ripples, allows us to hear the echoes of cosmic collisions. In conclusion, the journey from theoretical prediction to observational confirmation of neutron stars is a testament to the power of scientific inquiry. It highlights how theoretical foresight, combined with technological innovation and serendipitous discovery, can unlock the deepest secrets of the universe. The calm cosmos, in its slow unveiling, continues to reward our curiosity, inviting us to explore the profound implications of these cosmic wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now explore the intriguing possibility of using neutron stars as natural laboratories for fundamental physics, pushing the boundaries of our understanding of gravity, quantum mechanics, and the very nature of space-time. Their extreme properties offer unique opportunities to test theories under conditions unattainable in terrestrial laboratories. The calm cosmos, in its cosmic extremes, provides unparalleled environments for scientific discovery. One of the most significant roles of neutron stars in fundamental physics is their ability to test Einstein's theory of general relativity in the strong field regime. General relativity has been remarkably successful in describing gravity on solar system scales, but its predictions in extremely strong gravitational fields, like those near neutron stars or black holes, are still being rigorously tested. Pulsars, with their incredibly precise timing, are ideal tools for these tests. The calm cosmos, in its gravitational embrace, offers a proving ground for our theories. For example, the Hulse-Taylor binary pulsar, PSRB 1913+16, discovered in 1974, consists of two neutron stars orbiting each other. The precise timing of its pulses allowed astronomers to observe the gradual decay of its orbit due to the emission of gravitational waves, exactly as predicted by general relativity. This was the first indirect evidence for gravitational waves, decades before their direct detection. This system continues to provide stringent tests of general relativity, confirming its predictions with remarkable accuracy. The calm cosmos, in its orbital dances, validates our understanding of gravity. Another system, the double pulsar PESAR-J 0737-3039A/B, discovered in 2003, consists of two active pulsars orbiting each other. This unique system allows for even more precise tests of general relativity, including the measurement of relativistic effects like Shapiro delay, the slowing down of light as it passes through a gravitational field, and the lens-thirring effect, frame dragging. The extreme precision of these measurements has provided some of the strongest constraints on alternative theories of gravity, demonstrating that general relativity remains the most accurate description of gravity in the strong field regime. The calm cosmos, in its cosmic laboratories, refines our understanding of space-time. Beyond general relativity, Neutron stars also offer a unique window into the realm of quantum chromodynamics, QCD, the theory that describes the strong nuclear force. The densities in the core of a neutron star are so immense that they push the limits of our understanding of how quarks and gluons behave under such extreme conditions. As discussed earlier, the precise equation of state of nuclear matter at these densities is still unknown, and observations of neutron stars, particularly their masses and radii, provide crucial constraints for theoretical models of QCD. The calm cosmos, in its ultimate compression, challenges our understanding of fundamental particles. For instance, the discovery of massive neutron stars with masses around 2 solar masses has ruled out many theoretical models that predicted softer equations of state. These observations suggest that nuclear matter is stiffer than previously thought, meaning it is more resistant to compression. This has profound implications for our understanding of the strong nuclear force and the behavior of quarks and gluons at extreme densities. The calm cosmos, in its cosmic scales, reveals the subtle properties of subatomic particles. Neutron stars also provide a unique environment for studying the interplay between gravity and quantum mechanics, a frontier where our current theories are incomplete. While general relativity describes gravity on large scales, and quantum mechanics describes the behavior of matter at small scales, a unified theory of quantum gravity remains elusive. Neutron stars, with their extreme gravity and quantum-dense matter, are natural laboratories for exploring this interface. The calm cosmos, in its fundamental mysteries, holds the key to a unified theory. For example, the behavior of superfluidity and superconductivity in neutron stars, as discussed earlier, is a macroscopic manifestation of quantum phenomena occurring in an extreme gravitational environment. Studying these phenomena can provide insights into how quantum effects are modified or enhanced by strong gravity. The calm cosmos, in its paradoxical conditions, offers clues to the nature of quantum gravity. Furthermore, the search for exotic particles and phases of matter within neutron star cores, such as hyperons or quark-gluon plasma, is directly linked to fundamental particle physics. If these exotic states exist, their detection or inference from neutron star observations would provide crucial experimental evidence for theories beyond the standard model of particle physics. The calm cosmos, in its deepest secrets, might harbour new forms of matter. In conclusion, neutron stars are not just fascinating astronomical objects, they are invaluable cosmic laboratories for testing the fundamental laws of physics under conditions that cannot be replicated on Earth. From rigorous tests of general relativity to probing the behaviour of nuclear matter at extreme densities, and exploring the interface between gravity and quantum mechanics, these objects continue to push the boundaries of our scientific understanding. The calm cosmos, in its cosmic extremes, provides unparalleled environments for scientific discovery, inviting us to explore the profound implications of these celestial wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now explore the intriguing connection between neutron stars and the enigmatic phenomenon of fast radio bursts, FRBS. These incredibly powerful, millisecond duration radio flashes originate from distant galaxies, and their true nature has been one of the most perplexing mysteries in astrophysics. Recent discoveries, however, strongly suggest that at least some FRBS are generated by magnetars, a type of neutron star with incredibly strong magnetic fields. The calm cosmos, in its sudden outbursts, reveals the power of these extreme objects. Fast radio bursts were first discovered in 2007, when a single powerful radio pulse was found in archival data from the Parkes Observatory in Australia. Since then, thousands of FRBS have been detected by radio telescopes around the world. Their defining characteristics are their extremely short duration, typically a few milliseconds, and their immense brightness, implying that their sources must be incredibly energetic. The calm cosmos, in its fleeting signals, challenges our understanding of cosmic phenomena. One of the most puzzling aspects of FRBS was their extragalactic origin. The dispersion measure of the radio pulses, the delay in arrival time of different frequencies due to their interaction with free electrons in space, indicated that they had travelled vast distances, traversing billions of light years to reach Earth. This meant that whatever was producing them had to be incredibly powerful, far more energetic than any known terrestrial or galactic radio source. The calm cosmos, in its vast distances, amplifies the mystery of these bursts. For years, the progenitors of FRBS remained a mystery, leading to a wide range of speculative theories, from exotic astrophysical phenomena to even extraterrestrial intelligence. However, the discovery of repeating FRBS, where multiple bursts originate from the same location, began to narrow down the possibilities. This suggested that the source was not a single, cataclysmic event, but rather an object that could repeatedly produce these powerful flashes. The calm cosmos, in its recurring signals, provided a crucial clue. The breakthrough came in April 2020, when a fast radio burst, FRB 2020-0428A, was detected originating from within our own Milky Way galaxy. This was a game-changer because it allowed astronomers to pinpoint the source to a known object, a magnetar named SGR 1935+2154. This magnetar had been known to produce X-ray and gamma-ray bursts, but this was the first time it was observed to emit a powerful radio burst consistent with an FRB. The calm cosmos, in its galactic proximity, revealed the smoking gun. This discovery provided compelling evidence that at least some FRBS are indeed generated by magnetars. The mechanism by which magnetars produce these incredibly powerful radio bursts is still a subject of active research, but it is thought to involve processes related to their extreme magnetic fields, such as magnetic reconnection events or starquakes that trigger coherent radio emission. The calm cosmos in its magnetic fury unleashes bursts of radio energy. However, the magnetoconnection doesn't necessarily explain all FRBS. There are still many non-repeating FRBS, which could originate from different types of sources, such as the merger of two neutron stars or the collapse of a massive star into a black hole. It is likely that FRBS are a diverse population, with multiple astrophysical origins. The calm cosmos, in its complexity, often has multiple explanations for its phenomena. The study of FRBS is a rapidly evolving field, with new discoveries being made regularly. Dedicated FRB telescopes, like CHIME in Canada, are detecting hundreds of new bursts, allowing astronomers to build large statistical samples and study their properties in detail. These observations are providing crucial insights into the extreme physics of neutron stars, the properties of the intergalactic medium, and even the expansion history of the universe. The calm cosmos, in its fleeting signals, offers a new probe of cosmic distances. In conclusion, the connection between fast radio bursts and magnetars represents a significant breakthrough in astrophysics, shedding light on one of the most enigmatic phenomena in the universe. While the full picture of FRB origins is still unfolding, the role of neutron stars, particularly magnetars, is becoming increasingly clear. The calm cosmos, in its sudden outbursts, continues to reveal the power and mystery of these extreme objects, inviting us to explore the profound implications of these cosmic wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now consider the ultimate fate of neutron stars and their potential transformation into even more enigmatic objects: black holes. While neutron stars represent the densest stable objects in the universe, there's a limit to how much mass they can support. Beyond this limit, even the immense neutron degeneracy pressure succumbs to the relentless pull of gravity, leading to a complete gravitational collapse and the formation of a black hole. The calm cosmos, in its gravitational extremes, reveals the ultimate destiny of massive stellar remnants. The maximum mass a neutron star can sustain is known as the Tolman-Oppenheimer-Volkoff limit. The exact value of this limit is still a subject of active research, and depends critically on the equation of state of nuclear matter at extreme densities. Current estimates place the TOV limit somewhere between 2 and 3 solar masses. If a star's core, after a supernova explosion, is more massive than this limit, it cannot form a stable neutron star. Instead, it will continue to collapse, forming a stellar mass black hole. The calm cosmos, in its fundamental laws, sets the boundaries for stellar remnants. There are several scenarios in which a neutron star might exceed the TOV limit and collapse into a black hole. One common scenario is through accretion in a binary system. If a neutron star is part of a binary system with a companion star, it can pull matter from its companion, gradually increasing its mass. As the neutron star accretes more and more mass, it approaches the TOV limit. Once it crosses this threshold, the neutron degeneracy pressure can no longer support the star against its own gravity, and it collapses to form a black hole. This process is thought to be responsible for some of the observed stellar mass black holes in binary systems. The calm cosmos, in its gravitational dances, orchestrates the birth of black holes. Another scenario involves the merger of two neutron stars. As we discussed earlier, binary neutron star mergers are powerful sources of gravitational waves and are responsible for producing heavy elements. When two neutron stars spiral inward and collide, the resulting object can be more massive than the TOV limit. In such cases, the newly formed hypermassive neutron star will rapidly collapse into a black hole, often within milliseconds, emitting a final burst of gravitational waves and possibly a short gamma-ray burst. The calm cosmos, in its violent unions, witnesses the creation of space-time singularities. The transition from a neutron star to a black hole is a fascinating theoretical process. As the neutron star's core collapses beyond the point where neutron degeneracy pressure can hold it up, the matter becomes so dense that it forms a singularity, a point of infinite density and zero volume. Around this singularity, a region of space-time forms from which nothing, not even light, can escape. This boundary is known as the event horizon, and it defines the black hole. The calm cosmos, in its ultimate compression, creates regions of no return. Observational evidence for this transition is indirect but compelling. The detection of gravitational waves from binary neutron star mergers, where the remnant is inferred to be a black hole, provides strong support for this process. Furthermore, the existence of stellar mass black holes with masses greater than the TOV limit, often found in X-ray binary systems, is consistent with the idea that they formed from the collapse of massive neutron stars. The calm cosmos, in its observational clues, confirms the theoretical predictions. The study of the neutron star black hole transition is crucial for understanding the extreme physics of gravity and the nature of space-time. It allows us to probe the limits of matter and the conditions under which it can no longer resist the pull of gravity. It also helps us understand the formation mechanisms of stellar mass black holes, which are important components of galactic ecosystems. The calm cosmos, in its gravitational extremes, pushes the boundaries of our physical understanding. In conclusion, while neutron stars are incredibly dense and exotic objects, they are not the final stage for all massive stellar remnants. If they accrete too much mass or merge with another neutron star, they can cross the Tolman-Oppenheimer-Volkoff limit and collapse into black holes, the ultimate gravitational prisons. This transition represents a profound moment in the life cycle of massive stars where matter succumbs entirely to gravity, creating space-time singularities that continue to challenge our understanding of the universe. The calm cosmos, in its gravitational extremes, reveals the ultimate destiny of massive stellar remnants, inviting us to explore the profound implications of these cosmic transformations for the nature of reality and our place within its ever-unfolding narrative. Let's now consider the intriguing, albeit highly speculative question of whether neutron stars could somehow be involved in, or even host exotic forms of life, while the conditions on and around neutron stars are unimaginably extreme, pushing the boundaries of what we consider habitable. The vastness and strangeness of the cosmos often challenge our anthropocentric assumptions about life. The calm cosmos, in its boundless diversity, might harbour life in forms we can barely conceive. Our conventional understanding of life, as we know it on Earth, requires liquid water, a stable energy source, and a relatively benign environment with moderate temperatures and pressures. Neutron stars, with their crushing gravity, extreme temperatures, initially, intense radiation, and powerful magnetic fields, seem to be the antithesis of a habitable environment. The surface gravity is so strong that a human would be instantly flattened to a thin film, and the radiation would sterilize anything organic. The calm cosmos, in its harsh realities, presents environments seemingly hostile to life. However, the concept of exotic life extends beyond our carbon-based, water-dependent paradigm. Scientists and astrobiologists have speculated about life forms that could exist in environments vastly different from Earth. For instance, some theories propose life based on silicon instead of carbon, or life that thrives in liquid methane or ammonia instead of water. But even these alternative chemistries would struggle to survive the sheer extremes of a neutron star. The calm cosmos, in its theoretical possibilities, pushes the boundaries of biological imagination. One highly speculative idea involves the possibility of nuclear life within the core of a neutron star. This concept, often bordering on science fiction, suggests that under the immense pressures and densities, complex structures could form from nuclear matter, perhaps exhibiting self-organization and replication. However, there is currently no scientific evidence or theoretical framework to support such a notion, and the timescales for such processes would likely be incredibly short due to the rapid cooling and dynamic nature of the neutron star interior. The calm cosmos, in its deepest mysteries, remains silent on the existence of nuclear life. A more plausible, though still extremely speculative, scenario might involve the very distant future of neutron stars. As neutron stars cool over billions and trillions of years, their surface temperatures would eventually drop to a point where some form of exotic chemistry might become possible on their surfaces, assuming some form of atmosphere could be retained. However, even then, the immense gravity and radiation would pose formidable challenges. The calm cosmos, in its distant future, might witness new forms of existence. Perhaps the most intriguing, and slightly less fantastical, connection between neutron stars and life lies not in the neutron stars themselves, but in the events that create them and the elements they forge. As we discussed, supernovae and neutron star mergers are the primary cosmic factories for the production of heavy elements, including those essential for life as we know it, such as carbon, oxygen, and especially the heavy metals like iron, which is crucial for hemoglobin in our blood, and gold and platinum, which are formed in colonovae. Without these cataclysmic events, the raw ingredients for planets and life would not exist in the abundance we observe. The calm cosmos, in its violent creation, provides the building blocks of life. In this sense, neutron stars are indirectly vital for life. Their violent birth and subsequent mergers are part of the grand cosmic cycle that enriches the universe with the necessary elements for complex chemistry and biological evolution. So, while a neutron star itself is an unlikely abode for life, the processes that lead to its formation and the events it participates in are fundamental to the existence of life elsewhere in the cosmos. The calm cosmos, in its intricate web of cause and effect, demonstrates the profound interconnectedness of all cosmic phenomena. Furthermore, the extreme conditions around neutron stars, particularly the powerful magnetic fields and intense radiation, could potentially be harnessed by incredibly advanced civilizations. While this is pure speculation, some science fiction concepts explore the idea of civilizations living near or even on neutron stars, utilizing their immense energy output or unique physical properties. However, such concepts are far beyond our current understanding of physics and engineering. The calm cosmos, in its theoretical frontiers, invites us to imagine the unimaginable. In conclusion, while the direct existence of life on or within neutron stars remains firmly in the realm of science fiction and extreme speculation, these enigmatic objects play an undeniable, albeit indirect, role in the cosmic story of life. Their formation and mergers are crucial for the creation and dispersal of the heavy elements that are the very building blocks of planets and biological organisms. The calm cosmos, in its boundless diversity, might harbour life in forms we can barely conceive, but it is through the violent deaths of massive stars that the seeds of life are sown across the universe. It is a reminder that the more we learn about the universe, the more we realise how much more there is to discover and how deeply interconnected we are with the fundamental fabric of reality. Let's now explore the intriguing possibility of using neutron stars as cosmic laboratories for understanding the early universe and the fundamental forces that shaped it. While neutron stars themselves are formed much later in cosmic history, the extreme conditions within them can mimic, in some ways, the conditions that existed just moments after the Big Bang. The calm cosmos, in its extreme remnants, offers a unique window into its primordial past. The early universe, in the first few microseconds after the Big Bang, was incredibly hot and dense. At these extreme temperatures and pressures, matter existed in a state known as a quark-gluon plasma, where quarks and gluons, the fundamental constituents of protons and neutrons, were deconfined and moved freely. As the universe expanded and cooled, these quarks and gluons condensed to form protons and neutrons, a process known as the QCD phase transition. The calm cosmos, in its infancy, underwent profound transformations. The densities in the core of a neutron star, particularly in its innermost regions, can reach several times that of normal atomic nuclei. At these densities, it is theorized that matter might again undergo a phase transition, potentially forming a quark-gluon plasma or other exotic states of matter such as hyperons, particles containing strange quarks. If such exotic phases exist within neutron stars, studying their properties could provide crucial insights into the behavior of matter under conditions similar to those of the early universe. The calm cosmos, in its ultimate compression, might recreate the conditions of its birth. For example, the equation of state, EOS, of nuclear matter, which describes the relationship between pressure and density, is a key parameter in both neutron star physics and early universe cosmology. By precisely measuring the masses and radii of neutron stars, astronomers can constrain the EOS, which in turn can inform models of the QCD phase transition and the evolution of the early universe. The calm cosmos in its cosmic laboratories allows us to test the limits of our physical theories. Furthermore, the strong magnetic fields of neutron stars, particularly magnetars, might also offer clues about the early universe. Some theories suggest that the universe generated strong magnetic fields in its earliest moments, which could have influenced its subsequent evolution. While direct evidence for these primordial magnetic fields is elusive, studying the origin and evolution of magnetic fields in extreme astrophysical objects like neutron stars can provide insights into the mechanisms that generate and amplify magnetic fields in the cosmos. The calm cosmos in its magnetic embrace might hold secrets of its primordial magnetism. Neutron stars also play a role in the cosmic ray puzzle. Cosmic rays are high-energy particles that bombard Earth from space. While their exact origin is still debated, some theories suggest that supernovae and their remnants, including neutron stars, could be sources of these energetic particles. Understanding the acceleration mechanisms around neutron stars could shed light on the origin of cosmic rays, which in turn can provide information about the extreme processes occurring in the universe. The calm cosmos, in its energetic particles, sends us messages from its most violent events. In conclusion, while neutron stars are products of stellar evolution, their extreme conditions make them invaluable cosmic laboratories for probing the fundamental laws of physics and understanding the early universe. From the behavior of matter at supernuclear densities to the generation of strong magnetic fields and the acceleration of cosmic rays, these objects offer unique insights into the most extreme phenomena in the cosmos. The calm cosmos, in its extreme remnants, offers a unique window into its primordial past, inviting us to explore the profound implications of these celestial wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now explore the fascinating future of neutron star research, driven by new observatories, advanced theoretical models, and the promise of multi-messenger astronomy. The calm cosmos, in its boundless mysteries, continues to inspire our scientific endeavours, pushing the boundaries of human knowledge. One of the most exciting frontiers is the continued development of gravitational wave observatories. While LIGO and Virgo have revolutionized the field, next-generation detectors like the Cosmic Explorer and the Einstein telescope are planned to be significantly more sensitive. These instruments will be able to detect neutron star mergers from much greater distances, encompassing a larger volume of the universe. This will lead to a dramatic increase in the number of detected events, allowing for more robust statistical studies of neutron star populations, their merger rates, and the distribution of heavy elements in the cosmos. The calm cosmos, in its gravitational ripples, awaits our enhanced listening. Furthermore, these advanced gravitational wave detectors will provide more precise measurements of the gravitational wave signals, allowing scientists to extract even more detailed information about the properties of the merging neutron stars, such as their masses, spins, and tidal deformabilities. Tidal deformability, in particular, is directly related to the equation of state of nuclear matter, offering a unique way to probe the extreme physics of neutron star interiors. The calm cosmos, in its subtle vibrations, holds clues to its fundamental nature. Beyond ground-based detectors, the development of space-based gravitational wave observatories, such as the Laser Interferometer Space Antenna LISA, will open up the low-frequency gravitational wave spectrum. While LISA will primarily target supermassive black hole mergers, it will also be sensitive to other exotic sources, potentially including very early-stage and spirals of binary neutron stars, or even gravitational waves from the early universe. The calm cosmos, in its vastness, promises new revelations through the lens of gravitational waves. In the realm of electromagnetic astronomy, new and upgraded telescopes across the spectrum will continue to provide complementary insights. Next-generation X-ray observatories, like the Athena X-ray Observatory, will offer unprecedented sensitivity and resolution, allowing us to study the surfaces and atmospheres of neutron stars in greater detail, and to probe the physics of accretion onto these compact objects. This will help us understand the cooling mechanisms of neutron stars, the properties of their crusts, and the dynamics of their magnetospheres. The calm cosmos, in its X-ray glow, promises new insights into the hot and energetic lives of neutron stars. Radio astronomy is also undergoing a renaissance with the development of large arrays like the Square Kilometre Array, SKA. The SKA, with its unparalleled sensitivity and survey speed, will be able to detect fainter and more distant pulsars, potentially discovering thousands of new neutron stars. This will significantly expand our sample size, allowing for more comprehensive studies of pulsar populations, their evolution, and their role in galactic dynamics. The SKA will also be crucial for detecting new types of pulsars and for conducting even more precise timing experiments, further refining tests of general relativity. The calm cosmos, in its radio whispers, awaits our enhanced listening. Neutrino astronomy, though still in its nascent stages for astrophysical sources beyond the Sun and supernova 1987A, holds immense promise for understanding neutron stars. Detecting neutrinos from supernovae would provide direct information about the core collapse process, which is currently hidden from electromagnetic observation. Furthermore, future neutrino detectors might even be able to detect neutrinos from neutron star mergers, offering another unique probe of these extreme events. The calm cosmos, in its elusive particles, offers another window into extreme cosmic events. Beyond observations, theoretical and computational astrophysics will continue to play a vital role. Supercomputer simulations are becoming increasingly sophisticated, allowing scientists to model the complex processes of supernova explosions, neutron star formation, and binary neutron star mergers with unprecedented detail. These simulations are crucial for interpreting observational data, making predictions for future observations and pushing the boundaries of our theoretical understanding of matter under extreme conditions. The calm cosmos, in its computational models, allows us to recreate its most violent phenomena. Finally, the interdisciplinary nature of neutron star research will continue to flourish. The insights gained from studying neutron stars will feed back into nuclear physics, particle physics, and cosmology, helping to refine our understanding of the fundamental forces and particles that govern the universe. The calm cosmos, in its intricate web of knowledge, fosters interdisciplinary collaboration. In conclusion, the future of neutron star research is incredibly bright, promising a wealth of new discoveries and profound insights into the most extreme objects in the universe. With new observatories coming online, advanced theoretical models being developed, and the power of multi-messenger astronomy, our understanding of these cosmic wonders will continue to expand, pushing the boundaries of human knowledge and inspiring new generations of scientists. The calm cosmos, in its boundless mysteries, continues to inspire our scientific endeavours, inviting us to explore the profound implications of these celestial wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now explore the intriguing role of neutron stars in the context of extreme astrophysical phenomena, beyond just their formation and mergers. These compact objects are often at the heart of some of the most energetic and mysterious events in the universe, serving as cosmic engines that power incredible displays of light and radiation. The calm cosmos, in its violent grandeur, showcases the power of these stellar remnants. One such phenomenon is the X-ray burst. These are sudden, intense flashes of X-rays that originate from neutron stars in binary systems. When a neutron star accretes matter from a companion star, hydrogen and helium accumulate on its surface. As this layer grows, the temperature and pressure at its base increase, until the hydrogen and helium undergo runaway thermonuclear fusion, similar to a hydrogen bomb. This explosion releases an enormous amount of energy in a matter of seconds, producing a bright X-ray burst. These bursts are incredibly luminous, briefly outshining the entire star system, and provide valuable insights into the nuclear physics of extreme densities. The calm cosmos, in its stellar explosions, reveals the power of surface fusion. Another related phenomenon is the superburst. These are much rarer and more energetic X-ray bursts, lasting for hours instead of seconds. Superbursts are thought to be caused by the ignition of a deeper layer of carbon on the neutron star's surface, which has accumulated over months or years. The energy released in a superburst is immense, equivalent to the Sun's total energy output over several decades. Studying superbursts helps us understand the composition of the neutron star's crust and the conditions under which these deep thermonuclear runaway events occur. The calm cosmos, in its deep-seated fires, unleashes colossal energy. Neutron stars are also implicated in the generation of gamma-ray bursts, GRBS, the most powerful explosions in the universe. While long GRBs, lasting more than 2 seconds, are generally associated with the collapse of very massive stars into black holes, short GRBs, lasting less than 2 seconds, are now strongly linked to the merger of 2 neutron stars, or a neutron star and a black hole. These mergers produce a relativistic jet of material that, when pointed towards Earth, creates a powerful burst of gamma rays. The multi-messenger observation of GW 170817, the binary neutron star merger, confirmed this link, as it was accompanied by a short GRB. The calm cosmos, in its cosmic fireworks, illuminates the most violent events. Beyond these transient events, neutron stars are also responsible for powering some of the most persistent and luminous X-ray sources in galaxies, known as ultraluminous X-ray sources, ULXS. While some ULXs are thought to be intermediate mass black holes, a significant fraction are now believed to be neutron stars accreting matter at super-Eddington rates. This means they are accreting matter at a rate that exceeds the theoretical limit at which radiation pressure would blow away the infalling material. Understanding how neutron stars can sustain such high accretion rates challenges our current models of accretion physics. The calm cosmos, in its luminous displays, pushes the boundaries of accretion theory. Neutron stars are also key players in the dynamics of globular clusters, dense spherical collections of hundreds of thousands of stars. Due to the high stellar densities in these clusters, neutron stars frequently encounter and interact with other stars, leading to the formation of exotic binary systems. These interactions can spin up pulsars to millisecond periods, create X-ray binaries, and even lead to the formation of low-mass X-ray binaries, LMXBS, where a neutron star accretes matter from a low-mass companion. The calm cosmos, in its crowded clusters, fosters unique stellar interactions. Furthermore, the powerful magnetic fields of neutron stars, particularly magnetars, can have far-reaching effects on the surrounding interstellar medium. The sudden release of magnetic energy during magnetar flares can create powerful shock waves that propagate through space, heating and ionizing the gas. These events contribute to the overall energy budget of galaxies and can influence star formation in nearby regions. The calm cosmos, in its magnetic dominance, shapes its galactic environment. In conclusion, neutron stars are not just passive remnants of stellar death. They are active participants in the universe's most extreme phenomena. From powering X-ray bursts and superbursts to generating gamma-ray bursts and ultraluminous X-ray sources, and influencing the dynamics of globular clusters, these compact objects are cosmic engines that drive incredible displays of light and radiation. The calm cosmos, in its violent grandeur, showcases the power of these stellar remnants, inviting us to explore the profound implications of these cosmic wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now delve into the theoretical challenges and open questions that continue to drive research in the field of neutron stars. Despite significant advancements in both observation and theory, these extreme objects still hold many mysteries, pushing the boundaries of our current understanding of physics. The calm cosmos, in its deepest secrets, invites us to unravel its most profound enigmas. One of the most significant open questions revolves around the precise equation of state of nuclear matter at the extreme densities found in neutron star, cause. As discussed earlier, the EOS dictates the relationship between pressure and density, and it determines the star's internal structure, its maximum mass, and its radius. While observations of neutron star masses and radii provide crucial constraints, there is still considerable uncertainty about the exact composition and behavior of matter at densities several times that of an atomic nucleus. Do hyperons exist in the core? Is there a phase transition to a quark-gluon plasma? These questions remain unanswered, and their resolution would have profound implications for nuclear physics and our understanding of the strong force. The calm cosmos, in its ultimate compression, challenges our understanding of fundamental forces. Another major challenge is understanding the precise mechanisms behind the supernova explosion itself. While the general picture of core collapse and shockwave propagation is established, the details of how the shockwave is re-energized and successfully expels the outer layers of the star are still not fully understood. Neutrinos are thought to play a crucial role, but the complex interplay of hydrodynamics, nuclear physics, and neutrino transport makes it a formidable computational problem. A better understanding of supernovae would not only shed light on neutron star formation, but also on the origin of many elements in the universe. The calm cosmos, in its violent birth, holds secrets of its explosive power. The evolution of magnetic fields in neutron stars is another area of active research. While we know that neutron stars possess incredibly strong magnetic fields, the exact mechanisms by which these fields are generated and how they evolve over time are still debated. Are they fossil fields from the progenitor star, or are they generated by dynamo processes within the neutron star itself? How do these fields decay, and what causes the extreme outbursts of magnetars? Answering these questions would provide insights into fundamental plasma physics and the behavior of matter in extreme magnetic environments. The calm cosmos, in its magnetic embrace, hides the origins of its immense fields. Pulsar glitches, the sudden spin-ups observed in some pulsars, also present an ongoing mystery. While they are generally attributed to the sudden transfer of angular momentum from a superfluid interior to the solid crust, the precise trigger and dynamics of these events are not fully understood. Studying glitches can provide unique insights into the superfluid properties of neutron star interiors and the coupling between different layers of the star. The calm cosmos, in its cosmic gyroscopes, reveals subtle clues to its internal dynamics. The nature of fast radio bursts, FRBS, remains a significant puzzle, despite the strong evidence linking some of them to magnetars. Are all fast radio bursts produced by magnetars, or are there other progenitors? What are the precise emission mechanisms that generate these incredibly powerful radio flashes? How can they be so bright and so short? Understanding FRBS could lead to breakthroughs in our understanding of extreme astrophysical plasmas and the conditions in distant galaxies. The calm cosmos, in its fleeting signals, continues to challenge our understanding of cosmic phenomena. Finally, the precise mass and radius measurements of neutron stars are crucial for constraining theoretical models, but they remain challenging to obtain with high accuracy. Future observatories, particularly next-generation X-ray telescopes and gravitational wave detectors, are expected to provide more precise measurements, which will be vital for narrowing down the possible equations of state and understanding the internal structure of these objects. The calm cosmos, in its subtle variations, provides clues to its fundamental nature. In conclusion, despite decades of research, neutron stars continue to be a source of profound mysteries and open questions. Their extreme properties make them unique laboratories for testing the fundamental laws of physics under conditions that cannot be replicated on Earth. The calm cosmos, in its deepest secrets, invites us to unravel its most profound enigmas, pushing the boundaries of our understanding and encouraging us to explore alternative frameworks for comprehending existence. It is a reminder that the more we learn about the universe, the more we realize how much more there is to discover and how deeply interconnected we are with the fundamental fabric of reality. Let's now explore the profound significance of neutron stars in the broader context of cosmology and our understanding of the universe's evolution. These compact objects, born from the death of massive stars, are not just fascinating in their own right. They serve as crucial probes for understanding the fundamental properties of the cosmos, from its expansion rate to the distribution of matter and the nature of dark energy. The calm cosmos, in its grand design, reveals its secrets through these extreme remnants. One of the most direct cosmological applications of neutron stars comes from the study of binary neutron star mergers and their associated gravitational wave signals. As discussed earlier, The multi-messenger observation of GW 1708-17 provided a unique opportunity to measure the Hubble constant, the rate at which the universe is expanding. By combining the gravitational wave signal, which provides a direct measure of the luminosity distance to the merger, with the electromagnetic counterpart, which provides the redshift, a measure of the recession velocity, scientists can obtain an independent and precise measurement of the Hubble constant. This is crucial for resolving the current tension in cosmology, where different methods of measuring the Hubble constant yield slightly different values. Future gravitational wave observatories, with their increased sensitivity, will detect many more such events, allowing for even more precise cosmological measurements. The calm cosmos in its gravitational ripples helps us chart the universe's destiny. Neutron stars also play a role in understanding the distribution of matter in the universe. The formation of neutron stars is intimately linked to the star formation history of galaxies. By studying the distribution and properties of neutron stars, particularly pulsars, we can gain insights into the past rates of star formation and the evolution of stellar populations in different galactic environments. This helps us build a more complete picture of how galaxies form and evolve over cosmic time. The calm cosmos, in its stellar nurseries, reveals the history of its matter. Furthermore, the extreme densities within neutron stars provide a unique laboratory for probing the nature of dark matter. While dark matter does not interact electromagnetically, it is thought to interact gravitationally. Some theoretical models propose that dark matter particles could accumulate within neutron stars, potentially affecting their properties, such as their cooling rates or their maximum mass. Detecting such effects would provide crucial indirect evidence for the existence and properties of dark matter, one of the biggest mysteries in modern cosmology. The calm cosmos, in its hidden components, might reveal the secrets of dark matter through its densest objects. The study of neutron stars also contributes to our understanding of the origin of elements in the universe. As discussed, neutron star mergers are the primary cosmic factories for the heaviest elements, including gold, platinum, and uranium. These elements are then dispersed throughout the cosmos, becoming part of the raw material for new stars and planets. By precisely measuring the abundance of these elements in different cosmic environments and comparing them with theoretical predictions from kilonova models, we can refine our understanding of the chemical evolution of the universe. The calm cosmos, in its cosmic forge, creates the building blocks of complexity. Finally, neutron stars, as remnants of massive stars, are also important for understanding the feedback mechanisms in galactic evolution. Supernovae, which produce neutron stars, inject enormous amounts of energy and heavy elements into the interstellar medium. This energy can drive galactic winds, regulate star formation, and even influence the growth of supermassive black holes at galactic centers. By studying the impact of these energetic events, we can gain a deeper appreciation for the intricate interplay between individual stars and the large-scale structure of the universe. The calm cosmos, in its grand cycle, demonstrates the interconnectedness of all cosmic phenomena. In conclusion, neutron stars are far more than just exotic stellar remnants. They're invaluable cosmic probes that offer unique insights into the fundamental properties and evolution of the universe. From refining the Hubble, constant to shedding light on dark matter and understanding the origin of heavy elements, these extreme objects play a crucial role in shaping our cosmological understanding. The calm cosmos, in its grand design, reveals its secrets through these extreme remnants, inviting us to explore the profound implications of these celestial wonders for the nature of reality and our place within its ever-unfolding narrative. Let's now consider the intriguing and sometimes unsettling thought experiments and theoretical concepts that arise from the study of neutron stars. These objects push the boundaries of our imagination and force us to confront the most extreme possibilities of physics, leading to ideas that can sometimes feel like science fiction, but are grounded in the laws of the universe. The calm cosmos, in its theoretical extremes, invites us to ponder the truly bizarre. One such concept is the idea of a quark star or strange star. As discussed earlier, the core of a neutron star might contain a deconfined quark-gluon plasma, where quarks and gluons are no longer confined within individual protons and neutrons. A more radical idea is that if strange quark matter composed of up, down, and strange quarks, is more stable than ordinary nuclear matter, then some neutron stars might actually be strange stars, composed entirely of this exotic material. These hypothetical objects would be even denser than neutron stars and could have unique observational signatures. The calm cosmos, in its theoretical possibilities, expands our understanding of fundamental particles. Another thought experiment involves the concept of gravitational redshift and time dilation near neutron stars. Due to their immense gravity, time would pass more slowly for an observer near a neutron star compared to an observer far away. Similarly, light emitted from the surface of a neutron star would be gravitationally redshifted, meaning its wavelength would be stretched to longer, redder wavelengths. While these effects are predicted by general relativity and have been observed indirectly, the extreme conditions near neutron stars make them particularly pronounced, leading to fascinating theoretical scenarios. The calm cosmos, in its gravitational embrace, warps the very fabric of spacetime. Consider the idea of spaghettification near a neutron star. While typically associated with black holes, the tidal forces near a neutron star are still incredibly strong. If an object were to fall towards a neutron star, the gravitational pull on the part of the object closer to the neutron star would be significantly stronger than on the part farther away, stretching the object like spaghetti. While a human would be instantly destroyed by the immense gravity, the concept illustrates the extreme nature of the gravitational field. The calm cosmos, in its crushing embrace, demonstrates the power of tidal forces. Then there's the idea of pulsar planets. While most planets are thought to form around normal stars, the discovery of planets orbiting pulsars in the early 1990s was a complete surprise. These planets are thought to be either remnants of the original star system that survived the supernova, or they formed from a fallback disk of material after the supernova. The extreme radiation environment around a pulsar would make these planets incredibly hostile to life as we know it, but their existence demonstrates the unexpected ways in which planetary systems can form. The calm cosmos, in its unexpected formations, reveals the resilience of planetary systems. Another intriguing concept is the potential for gravitational lensing by neutron stars. While not as powerful as black holes, the immense gravity of a neutron star can bend the path of light passing near it. This can lead to phenomena where background objects appear distorted, magnified, or even multiple images of the same object are seen. Detecting such lensing events could provide another way to measure the mass of isolated neutron stars and test general relativity. The calm cosmos, in its gravitational distortions, plays tricks with light. Finally, the idea of neutron star engineering, or megastructures, is a purely speculative concept, often found in science fiction. This involves the hypothetical ability of an incredibly advanced civilization to manipulate the extreme properties of neutron stars for their own purposes, perhaps to extract energy, create exotic materials, or even build structures on their surfaces. While far beyond our current technological capabilities and understanding of physics, such ideas highlight the immense potential energy and resources locked within these compact objects. The calm cosmos, in its theoretical frontiers, invites us to imagine the unimaginable. In conclusion, the study of neutron stars not only pushes the boundaries of our observational and theoretical physics, but also inspires us to contemplate the most extreme and bizarre possibilities in the universe. From the existence of quark stars to the warping of space-time and the potential for cosmic engineering, these objects force us to expand our imagination and confront the limits of our current understanding. The calm cosmos, in its theoretical extremes, continues to challenge and expand our understanding of reality, inviting us to explore the profound implications of these cosmic wonders for the nature of existence and our place within its ever-unfolding narrative. In summary, neutron stars are truly extraordinary objects, born from the dramatic deaths of massive stars. They are cosmic laboratories where matter exists in states of unimaginable density, where gravity warps space-time to an extreme degree, and where the fundamental forces of the universe are put to the ultimate test. From their role as cosmic clocks and powerful magnetars, to their involvement in gravitational wave events and the creation of heavy elements, these stellar remnants continue to reveal the profound interconnectedness of the cosmos. Our journey through the world of neutron stars has taken us from their violent birth in supernova explosions to their exotic internal structures, where superfluidity and superconductivity reign. We've explored their diverse manifestations as pulsars, magnetars, and X-ray binaries, each offering unique insights into the extreme physics at play. we've seen how they serve as crucial probes for testing Einstein's theory of general relativity in the strong field regime, and how they contribute to our understanding of nuclear physics and the behaviour of matter at supernuclear densities. The advent of multi-messenger astronomy, particularly with the direct detection of gravitational waves from binary neutron star mergers, has opened an entirely new window into these objects, allowing us to observe cosmic events through both gravitational waves and electromagnetic radiation. This has not only confirmed long-standing theories, but has also provided unprecedented insights into the origin of heavy elements and the expansion rate of the universe. Looking ahead, the future of neutron star research is incredibly promising. New and upgraded observatories across the electromagnetic spectrum, coupled with next-generation gravitational wave detectors, will continue to push the boundaries of our understanding. Theoretical and computational astrophysics will also play a vital role, allowing us to model the complex processes of neutron star formation and evolution with ever-increasing precision. Ultimately, the study of neutron stars is a testament to the power of scientific inquiry and the human desire to understand the universe around us. These compact objects, in their extreme conditions, challenge our assumptions, expand our imagination, and deepen our appreciation for the intricate and often bizarre nature of reality. They remind us that even in the most violent and extreme corners of the cosmos, there is a profound beauty and order, a calm cosmos that continuously reveals its secrets to those who are willing to listen and observe. As we continue to explore these cosmic wonders, we're not just learning about distant stars, we're learning about the fundamental laws that govern our universe, the origins of the elements that make up our world and ourselves, and ultimately our place within the vast and ever-unfolding cosmic narrative. The calm cosmos, in its boundless mysteries, invites us to continue our journey of discovery, forever pushing the boundaries of what we know and what we can imagine. The study of neutron stars also extends to their potential as cosmic clocks and their role in precision astrophysics. Pulsars, with their incredibly stable and predictable rotation, are among the most precise natural clocks known. This extreme regularity allows astronomers to use them for a variety of high-precision measurements and tests of fundamental physics. The calm cosmos, in its cosmic precision, provides natural laboratories for fundamental physics. One of the most remarkable applications of pulsar timing is the search for gravitational waves. By precisely monitoring the arrival times of pulses from an array of millisecond pulses distributed across the galaxy, known as a pulsar timing array, PTA, scientists can detect subtle deviations caused by the passage of long wavelength gravitational waves. These gravitational waves are thought to be generated by the inspiral and merger of supermassive black holes at the centers of galaxies, providing a unique probe of the universe's most massive objects. The calm cosmos, in its gravitational symphony, plays a new tune for us to hear. PTAS are sensitive to gravitational waves with periods of years to decades, a frequency range that is complementary to ground-based interferometers like LIGO and VIRGO. This means that PTAS can detect gravitational waves from different types of sources, opening up a new window into the gravitational wave universe. The detection of a gravitational wave background by several PTAS in recent years has provided compelling evidence for the existence of these long wavelength ripples, hinting at a population of merging supermassive black holes throughout cosmic history. The calm cosmos, in its subtle vibrations, reveals the echoes of cosmic collisions. Beyond gravitational waves, pulsar timing also allows for incredibly precise measurements of stellar masses, orbital parameters, and even the properties of the interstellar medium. The slight delays or advances in pulse arrival times can be used to map the distribution of free electrons in the galaxy, providing insights into the structure and dynamics of the interstellar medium. The calm cosmos, in its cosmic signals, guides our understanding of galactic environments. Furthermore, the extreme gravitational fields of neutron stars make them ideal laboratories for testing the equivalence principle, a cornerstone of general relativity. The equivalence principle states that all objects fall with the same acceleration in a gravitational field, regardless of their mass or composition. By precisely timing pulses in binary systems with other compact objects, scientists can search for tiny deviations from this principle, which could indicate new physics beyond general relativity. The calm cosmos, in its gravitational embrace, offers a proving ground for our theories. In conclusion, The use of neutron stars as cosmic clocks and their application in precision astrophysics represent a powerful frontier in our quest to understand the universe. From detecting gravitational waves from supermassive black hole mergers to testing fundamental theories of gravity, these objects provide unparalleled opportunities for scientific discovery. The calm cosmos, in its cosmic precision, continues to reveal its profound secrets, inviting us to explore the profound implications of these celestial wonders, for the nature of reality and our place within its ever-unfolding narrative. Finally, let us reflect on the profound cultural impact and philosophical implications that neutron stars have had on human thought and our understanding of the cosmos. These extreme objects, born from the most violent events in the universe, challenge our intuitions about matter, gravity, and space-time, pushing the boundaries of human imagination and inspiring new ways of thinking about our place in the vast cosmic tapestry. The calm cosmos, in its most extreme manifestations, offers a mirror for our deepest inquiries. Neutron stars, with their unimaginable densities and powerful forces, serve as a powerful reminder of the universe's vastness and its capacity for phenomena far beyond our everyday experience. They force us to confront the limits of our physical intuition, where familiar concepts like solid matter and empty space cease to hold their conventional meaning. This intellectual challenge can be both humbling and exhilarating, expanding our mental horizons and encouraging us to embrace the bizarre and the extraordinary. The calm cosmos, in its strangeness, invites us to rethink our reality. Their discovery and the subsequent understanding of their properties have also had a significant impact on science fiction and popular culture. From stories exploring the possibility of life in extreme environments to narratives centered around the manipulation of their immense energy, neutron stars have become a staple of cosmic storytelling. They represent the ultimate frontier, a place where the laws of physics are pushed to their breaking point, offering fertile ground for imaginative exploration of humanity's future in the cosmos. The calm cosmos, in its fictional journeys, inspires dreams of interstellar exploration. Philosophically, neutron stars raise fundamental questions about the nature of reality itself. The existence of matter in such extreme states, where protons and electrons merge into a sea of neutrons, challenges our very definition of what constitutes matter. The fact that these objects are born from the death of massive stars and contribute to the creation of elements essential for life also highlights the cyclical and interconnected nature of the universe, where destruction can lead to new forms of creation. The calm cosmos, in its cosmic dance, reveals the profound interconnectedness of all things. Moreover, the study of neutron stars, particularly through gravitational waves, has opened up new avenues for understanding the fundamental forces of nature. The ability to test Einstein's theory of general relativity in the most extreme gravitational environments provides a deeper appreciation for the elegance and accuracy of our physical laws. It also reminds us that our understanding of the universe is constantly evolving, and there are always new frontiers to explore, new mysteries to unravel. The calm cosmos, in its gravitational embrace, continuously challenges and expands our understanding. In a broader sense, the existence of neutron stars underscores the idea that the universe is far stranger and more wonderful than we can often imagine. It encourages a sense of awe and wonder, prompting us to look beyond our terrestrial confines and contemplate the vastness and complexity of the cosmos. This sense of cosmic perspective can be both humbling and inspiring, reminding us of our small place in the universe while also highlighting the incredible capacity of the human mind to comprehend such profound phenomena. The calm cosmos, in its boundless mysteries, invites us to explore the depths of existence. Finally, the collaborative nature of neutron star research, involving scientists from around the globe working together to unravel these cosmic enigmas, reflects the universal human quest for knowledge. It demonstrates how shared curiosity and intellectual pursuit can transcend geographical and cultural boundaries, uniting humanity in a common endeavour to understand the universe we inhabit. The calm cosmos, in its shared exploration, fosters global collaboration. In conclusion, neutron stars are not just objects of scientific study. They are profound symbols of the universe's extreme nature and our ongoing journey to comprehend it. They challenge our assumptions, inspire our imaginations, and deepen our appreciation for the intricate and often bizarre nature of reality. The calm cosmos, in its most extreme manifestations, offers a mirror for our deepest inquiries, inviting us to explore the profound implications of these celestial wonders for the nature of reality and our place within its ever-unfolding narrative. It is a reminder that the more we learn about the universe, the more we realize how much more there is to discover, and how deeply interconnected we are with the fundamental fabric of reality.